You type a question into a chatbot and hit enter. Somewhere hundreds of miles away, a single chip burns about 3 watt-hours answering you. We are tracing that exact question keyboard to power plant. 3 watt-hours sounds like nothing. A Google search runs about 10. Charging your phone overnight is closer to 15. So one prompt is genuinely cheap. Here is the twist. People send hundreds of millions of these every single day. Multiply a tiny number by a giant one, and you get power plant scale demand. The whole story is about scale, not one question. Start where you do with the keyboard. Your question is just text. A typical prompt is a few hundred bytes, smaller than a single photo. Sending it across your Wi-Fi through your router down the fiber line. That energy is almost too small to measure. Think of it as a rounding error. The heavy lifting has not started yet. All your keyboard did was mail a tiny letter. That letter now races across the country to a data center. A warehouse packed wall-to-wall with computers, humming around the clock. Your prompt lands there as a request, one of millions arriving that second. And here is the part people miss. Nothing expensive has happened so far. The typing, the Wi-Fi, the fiber, call it zero. So if the network is basically free, where does the 3 watt-hours actually come from? To answer that, we have to walk inside the building. Inside the building, your prompt reaches a chip built for one job, doing enormous amounts of math at once. This is a graphics processor, a GPU. A high-end one, like NVIDIA's H100, can pull up to about 700 watts when it is working flat out. That is roughly 7 bright old-fashioned light bulbs, all burning inside one palm-sized chip. Now what is it actually doing? The AI model reads your words as small chunks, tokens. To write its reply, it produces one token at a time. Predicting each token means running the numbers through the model's memorized settings, called parameters. These models hold tens of billions of parameters. So a single word out of the chatbot can trigger billions of multiply and add steps. Then it does it again for the next word. And the next. Picture a stadium full of tiny calculators, all firing at once, thousands of times per second just to finish one sentence for you. This is the moment that matters. Not your typing, not the network. This raw computation is where nearly all the energy goes. The chip runs hot, the fans spin up, and the meter finally starts climbing. But watts are not the number on our thumbnail. Watts are a speed. To get watt-hours, we need to bring in time. That covers the how, now the how much. A 700-watt chip is a rate, like 700 miles per hour. It only becomes a distance once you know how long you drove. Your chatbot answers in a few seconds. Run 700 watts for a handful of seconds and you get on the order of a couple of watt-hours. Not the full 3 yet. So where does the rest come from? Here is the clever part. That chip almost never serves you alone. Data centers pack many people's questions onto the same GPU at the same time, a trick called batching. The chip was going to run anyway, so splitting its energy across a crowd keeps each person's slice low. Do the arithmetic across a busy batch, and a typical text prompt lands right around 3 watt-hours. 3 watt-hours, the number on the screen for one answer. But not every prompt is equal. A one-line factual reply, the capital of France, is cheaper because the chip stops sooner. Ask for a long, complex S, and it can cost several times more because it is generating far more tokens. And if you ask for an image or a video, that dwarfs text entirely. Same chip, same building, wildly different bills. Which raises an honest question, is 3 watt-hours even the whole story? Here is what the raw chip number quietly leaves out. The GPU does not float in space. It sits in a building that has to be kept cool, or it would cook itself in minutes. Those fans and chillers draw power too. So does the equipment that converts wall electricity into the exact form the chips need. Some energy is always lost in that conversion. Add the lights, the backup systems, the rack sitting idle waiting for work. Engineers track all of this with one tidy ratio. It compares the total power the building pulls to the power the chips alone actually use. That ratio is called PUE. A sloppy data center wastes a lot. A well-run modern one runs about 1.1 to 1.2. In plain terms, for every 10 units of energy the chips use, the building spends roughly 1 to 2 more just existing around them. So the honest number, the real draw at the wall, not just at the chip, sits a notch above that clean 3 watt-hours. Not double, not triple, but more than the GPU alone would suggest. We have now traced the energy from your keyboard to the chip to the whole building. One question left. Where was that electricity actually made? Now follow the wire out of the building. That electricity had to be generated somewhere. The grid feeding your data center is a mix: natural gas, some coal, nuclear, wind, solar. So the true footprint of your prompt is not really watt-hours. It is carbon. And the carbon depends entirely on where the data center sits. The same 3 watt-hours is nearly clean if it is pulled from a hydro-powered grid, and much dirtier if the plant next door burns coal. Same prompt, same chip, a different smokestack. There is one more cost hiding upstairs, and it is a big one. Before this model could answer a single question, it had to be built. That building phase, training, meant running thousands of these GPS for weeks or months straight, burning many gigawatt-hours of electricity. A gigawatt-hour is 1,000,000 times that watt-hour on your screen. It is an enormous one-time bill. But here is the saving grace. That training cost gets spread across every answer the model will ever give, billions and billions of them. Smear one giant number across a mountain of tiny ones, and each prompt's share of the training bill shrinks to almost nothing. So the day-to-day energy really is the inference, the answering, not the training. Which means we can finally put the whole chain back together. Let us reassemble the whole chain in one breath. Your keyboard, basically zero. The network carrying your words, basically zero. Then the GPU inference, the actual answering, that is the 3 watt-hour core where almost all the energy lives. Wrap the building around it, cooling, power conversion, idle gear, and the wall number climbs a notch above 3. Trace the wire home, and those watt-hours turn into carbon that depends on your local grid. That is the full journey, keyboard to power plant. Break time equals 0, 6 is / so here is the real answer, and it cuts both ways. One prompt is genuinely tiny, smaller than a Google search, a fraction of charging your phone. Feel free to ask your questions. But you are not one person. Hundreds of millions of people hit enter every day, and every single query spins up a chip in a hot building somewhere. Stack those rounding errors high enough and they stop being a rounding error. They become gigawatt hours. They become real steel, new power plants, built to feed the machine that answers you in seconds. So that is the 3 watt-hour journey. Keyboard, network, one hot GPU, the building around it, and the grid behind that. Next time you hit enter, remember it is tiny for you and enormous for all of us at once. If you want the next piece, how these data centers are racing to build their own power plants, subscribe and it is yours.